Welcome to this lecture on algebra. Today, we are going to explore a fascinating and incredibly useful mathematical tool called the generalized inverse. Have you ever tried to solve a problem where the perfect mathematical fit just does not exist? We will learn how to find the absolute best backup plan when traditional matrix division fails us. Let us dive in. Now that we know what our topic is, let us understand why we need it. In standard matrix algebra, finding an inverse is like finding a perfect pair of shoes. It only works if the matrix is perfectly square. But in the real world, data is messy, and we often deal with rectangular matrices that have a different number of rows and columns. These matrices refuse to cooperate and simply do not have a standard inverse. The generalized inverse is exactly the next best thing. It is a special mathematical tool that steps in when a perfect inverse does not exist, allowing us to solve complex equations and extract meaningful answers anyway. This brings us to the formal definition. The most famous generalized inverse is the Moore-Penrose inverse, denoted by A plus. Conceptually, it is defined by four strict geometric rules called the Penrose conditions. The first condition ensures that multiplying by the inverse and then the matrix again restores the original matrix. The second is the mirror image, ensuring the inverse does not carry unnecessary mathematical baggage. The third and fourth conditions involve the transpose, ensuring the resulting products are symmetric matrices. This symmetry is crucial for calculating distances properly. If any matrix A plus satisfies all four of these equations, it earns the title of the Moore-Penrose inverse. Now that we have defined the Penrose conditions, let us prove a beautiful property. The Moore-Penrose inverse is always completely unique. We are setting out to show that no matter what, there is only one valid inverse. We start with a clever trick. We pretend there are two different valid inverses. Let us call them B and C. Our goal is to prove they are actually the exact same matrix. Because B is a valid inverse, its product with A is symmetric, meaning A times B equals its own transpose. Using matrix algebra rules, we expand this. Then we substitute E with A times C times A, using the first condition for our other inverse C. This cleverly introduces C into our equation. Continuing our derivation, we take that long chain of transpose matrices and group them back together in pairs. This gives us the transpose of A times B multiplied by the transpose of A times C. Now, remember the third Penrose condition? It tells us that both of these products are symmetric. Because they are symmetric, they are equal to their own transposes, so we can just drop the transpose symbols entirely. This leaves us with A times B times A times C. Finally, we look at the first three terms. According to the first condition for B, A times B times A simply equals A. So the whole expression collapses, proving that A times B equals A times C. We are now ready for the final result. By following the exact same logical steps with the other conditions, we can also prove that B times A equals C times A. Now for the final strike. We start with the second condition for B, which states B equals B times A times B. We group the terms and swap them out using the facts we just proved. First, we replace A times B with A times C. Then, we regroup and replace B times A with C times A. This leaves us with C times A times C. According to the second condition for C, this simply equals C. We started with B and ended with C, proving they are the exact same matrix. So we have proven that this unique inverse exists. This brings us to a practical question. How do we actually calculate it? If our starting matrix has full column rank, meaning every column brings completely new, independent information, we can use this specific direct formula. Conceptually, we first multiply the transpose of the matrix by the original matrix. This creates a brand new, perfectly square matrix. Because it is square and has full rank, we can find its normal standard inverse. Finally, we multiply that standard inverse by the transpose of the original matrix. If the values in the original matrix change, the transpose and the resulting square matrix shift accordingly, adapting the generalized inverse to perfectly fit the new data. Before we move on, let us see this formula in action with a concrete example. We are given a simple rectangular matrix E, which is taller than it is wide. Because it has 3 rows and only 2 columns, it cannot have a normal inverse. We are asked to find its Moore-Penrose inverse. We chose our full column rank formula because the columns are independent. The first step is to find the transpose by flipping the rows into columns, turning it into a 2 by 3 matrix. Next, we multiply this transpose by the original matrix A. This careful arithmetic gives us a nice, neat 2 by 2 square matrix, which is exactly what we need for the next step. Continuing with our calculation, we now need to find the standard inverse of this new 2 by 2 square matrix. To do this, we use the standard rule. We swap the diagonal elements, change the signs of the off-diagonal elements, and divide everything by the determinant. The determinant here is 2 times 2 minus 1 times 1, which equals 3. So we divide the matrix by 3. Now we have the inverse of the product. The final step in our formula is to multiply this result by the transpose matrix from earlier. We set up the multiplication, leaving the 1/3 fraction on the outside for now, to keep the math clean and easy to follow. We are now at the final step. We perform the matrix multiplication by multiplying the rows of our square inverse by the columns of the transpose matrix. After calculating each element, we arrive at our final answer. We have successfully calculated the Moore-Penrose generalized inverse for our rectangular matrix. Physically, this resulting matrix represents the optimal mathematical pathway to reverse the effects of our original matrix A as closely as possible. If you were to test this final matrix against the 4 Penrose conditions we discussed earlier, it would pass every single one perfectly. Now that we have used this formula, let us understand where it is actually applied in the real world. Why do we go through all this trouble? The greatest superpower of the generalized inverse is solving overdetermined systems of linear equations. An overdetermined system is like trying to find a single meeting point for 3 friends standing in a wide triangle. They cannot all meet at exactly the same spot without someone walking further. In math, this means you have more equations than variables, making a perfect solution impossible. Instead of giving up, we look for the least squares solution. This is the mathematical equivalent of finding the spot in the middle that minimizes the total error for everyone. This brings us to the formula that makes finding that perfect compromise incredibly easy. In a standard system, we write A times X equals B. Since we cannot make the two sides perfectly equal, we measure the difference between them, which is our error. To find the absolute best minimum error solution for our variables x, all you have to do is multiply the target vector b by the Moore-Penrose inverse of A. Conceptually, the generalized inverse automatically calculates the perfect compromise. If the target values in vector b increase, the solution vector x shifts proportionally to maintain the absolute minimum possible error. It gives you the least square solution instantly. Before we calculate one, let us visualize exactly what the generalized inverse is doing geometrically. Look at the blue plane on your screen. This plane represents all the possible perfect solutions we can actually reach using our matrix. The red vector is our target B. Notice how it sits off the plane? That gap means a perfect solution is impossible. The generalized inverse solves this by dropping a perpendicular line straight down from the target to the plane. That dashed line is our error, and by dropping straight down at a 90-degree angle, it finds the green vector, the absolute closest possible point on the plane. This visually proves how it minimizes the error distance. Now that we understand the geometry, let us put this magic into practice. We are given an overdetermined system with 3 equations but only 2 variables. We are using the exact same matrix A from our previous example and a new target vector B. If you look closely at the equations, the first row says variable 1 is 1. The second says variable 2 is 1. But the third row says their sum should be 3. This is a direct contradiction, so a perfect solution is impossible. We chose the least squares formula to bypass these contradictions. We set up our strategy by multiplying the generalized inverse we already calculated by our new target vector. Let us finish the calculation. We write out the multiplication step by step to avoid mistakes. For the top row, we multiply and add the terms to get 2 minus 1 plus 3. For the bottom row, we get negative 1 plus 2 plus 3. Simplifying the addition inside, both rows sum up to 4. Finally, we multiply by the 1/3 scalar sitting outside to get our final values. This is our final least square solution. Physically, setting both variables to 4/3 is the absolute best possible compromise. It will not make any of the original 3 equations perfectly true, but it guarantees that the total squared error across the entire system is minimized. We have covered a lot of ground today, so let us summarize the most important ideas. First, the generalized inverse acts as a mathematical safety net, allowing us to work with rectangular matrices that lack a traditional inverse. Second, we learned that the Moore-Penrose inverse is completely unique, governed by the 4 strict Penrose conditions that preserve geometric symmetry. Finally, we saw how these concepts connect in the real world. Its greatest superpower is solving overdetermined systems. By finding the least square solution, it minimizes error when a perfect answer is impossible. You now understand the hidden engine powering much of modern data science and navigation. Great job today.